Okay, so let me start by distributing the formula sheet. If you don't have one, please pick one. And then these are the quality problems. So 1 page. So I'm just distributing the formula sheet and 1 page of quality problems. Okay. So does anybody have a question? Thank you. Does anybody have a question that you'd like me to go over or? Okay. So last time. We had to rush through.
Oh, I just have a question. So are we not going to be responsible for 8 or 9?
You're responsible for all of them.
But when we did the problems in class, we didn't do 8 or 9.
Yes, that's what I'm going to do today.
Okay.
So we couldn't finish up everything.
Okay.
So we're going to finish up everything. But if you had a question from before, question?
Yeah, more just logistics. Have you sent out the slide breakdown yet? Which slides to focus on?
I haven't written the questions yet, but as soon as I write the questions, I'll email everybody.
Okay.
Okay? Okay. So, last time, we kind of rushed through this. Today, I want to go over the P chart, okay, and C chart. I just hate this green board, but I hope you can at least somehow see this P chart and C chart. So, what is special about these? These are based on counts. Okay. These charts are based on counts. So you basically count defective items or number of defects. Okay? So question 5 says there are, so you take 4 samples, okay, and each sample has 200 credit card statements, and we inspect these credit cards. So within the first 200, we find 4 statements with errors. Okay, so 4 statements are defective out of a total of 200. In the first sample. In the second sample, 2 statements have errors. So 2 out of 200 are defective. In the third sample, 5 statements have errors. Okay? And in the fourth sample, 9 statements. And now, a statement can have 1 or more mistakes in it. Regardless of how many mistakes there is, we just count it as 1 defective statement. Okay? So here we have 2 defective statements. One statement can have 1 error. The other statement can have 100 errors. We don't care. It's just 2 defective statements out of 200. Okay? So this is the setup. So, this says, part A says determine the fraction defective in each sample. Okay? So we basically are going to divide each number by 200. So in the first sample, it's going to be 4 divided by 200, and then 2 divided by 200, 5 divided by 200, and 9 divided by 200. So let me pull this up. So in the first sample, so it's going to be 4 over 200. So this is going to be, I'm just drawing it blank. So 0.02 or 2%, okay, in the first sample. In the second sample, it's going to be 2 divided by 200. So that's going to be 0.01 or 1%. Okay. In the third sample, it's going to be 5 divided by 200, 0.025 or 2.5%. And then last sample, 9 divided by 200, 0.045 or 4.5%. So in each sample, we know exactly what percentage of statements are defective. Okay, so that's part A. Part B, now if the true fraction defective, okay, true fraction defective for this process is unknown. Okay, so there is a process that there's a computer program that prepares these statements, okay, and not all statements are 100% correct. Some of the statements have errors. So some of the statements produced by this computer program will be defective, but we don't know exactly what percent are defective. Okay, so then based on these percentages, what is our best guess? Okay, suppose, let's say we printed or prepared 1 million statements, 1 million credit card statements. Okay, what percent of these 1 million statements are defective? Okay, based on these percentages, 2%, 1%, 2.5%, 4.5%, based on these percentages, what would be our best guess?
Take the average?
Yes. Why? Now think about these. So we took 4 random samples. What are the chances that these samples are all above average? Or what are the chances that all of these samples are below average? Unlikely, right? So in the most likely scenario, some of them will be above average defective, some of them will be below average defective, because we pick them randomly. Okay? So the true fraction defective, our best guess, is the average of these 4 percentages. So what I do is I just, let me take the average here. So I have 2% plus 1% plus 2.5% plus 4.5% divided by 4, okay? The average of each sample's fraction defective, our best guess is 2.5% overall fraction defective. Yes.
Why don't we take the number of error like 4 plus 2 plus 5 plus 9 divided by 200 times 4?
Yes. Let's do that.
Yeah.
Wouldn't it be, well, isn't your sample size bigger? Because there's 200 in each one, so
Yes.
2 times 4.
Yeah. So let's see if we get a different result. So in the first one we have 4 plus 2 plus 5 plus 9 divided by 800. Right, so we have a total of 800 credit card statements. And then from the first sample we have 4 defective. From the second sample we have 2 defective. From the third sample we have 5 defective and then 9 defective. And you should actually get the same result. So you can do it both ways. You can do it both ways. Yes.
So it's called a fraction defective, but do you want us to give it to you as a percent?
Either one is fine. Either one is fine. So if you have like 1, that's fine. Okay. So if you do this, you're going to get 2.5%. If you do this, you're also going to get 2.5%. Yes.
But in the test, the question is still stay the same, right? Because sometimes it might confuse for me to understand about this question.
Yes. Okay. So on the exam, if you are confused, ask me. I will tell you which formula to use.
Okay.
Okay?
Yeah.
All right. So, okay. And then it says, what is your estimate of mean and standard deviation? Okay. So for that, we go to the formula sheet. So I'm just gonna. Okay. So these are the formulas. These are the formulas for the T-chart. Okay. This is the mean. This is the standard deviation. Okay. The mean. This is the mean. And this is the standard deviation. Okay. So then we have already calculated the mean, which is 2.5%, right? We have already calculated the mean because it says number of defective items divided by number of total items. So this is the number of defective items divided by the number of total items. So let's calculate the standard deviation. So the formula is square root of P, which is this P times 1 minus P, divided by the sample size. Okay. So let's do that here. So sigma sub P. 0.025 times 1 minus 0.025 divided by 200. Okay, so this is P, 0.025 is P, times 1 minus P, which is 1 minus 0.025, okay, and 200 is the sample size. Okay. Okay, so now we know what P is, and then what the standard deviation is, mean and standard deviation. Okay. 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 So what control limits, okay, would give an alpha risk of better this way. Okay. All right. So this question asks about the upper and lower control limits. Let me draw here. Erase this. Let me try this. Maybe this will work better. Okay. So the question is, which upper and lower control limit which upper and lower control limit would give us alpha risk of 0.03. So alpha risk means tail probabilities, so half of it will be on the right-hand side, 0.015 or 1.5%. So the total alpha risk will be 3%. Is this kind of better, or let me turn on the light maybe. Is this better?
Yeah.
Yes.
Okay. So here, this will be half of alpha, which is 0.015 or 1.5%, and this is the other half of alpha. Okay. So we want to find these upper and lower control limits. Okay. So we go from this normal distribution to standard normal. Okay. So there's going to be a z value that corresponds to the upper control limit, and another z value that corresponds to the lower control limit. Okay? So if this tail probability is 0.015, this will be also 0.015, yes, 0.015. Okay. And in the standard normal table, we're going to look for 1 minus 0.15, 0.985. Okay. So the tail probability is this much, 0.015. The table will show us 1 minus 0.015. Okay. And so let's look for that in the formula sheet. It's behind the formula sheet. So we're looking for point.
985.
Yeah. We're looking for this.
So in the table we look from to the left, right? Like the percentage from that point to the left.
Yes, we'll look for this to the left. Okay. 0.985. So which z value gives us 0.985? So we look at this 2.1, 2.10, 2.11, 12, 13, 14, 15, 16, 17. So this is going to be 2.17. So 2.10, 1, 2, 3, 4, 5, 6, 7. So the z value here gives us 0.985 and 0.015 tail probability. Does this make sense? Can everybody do this on the exam? Okay. So, how do we go from the z to the upper control limit? There's a formula on the formula sheet. Okay? And the formula says, yes. So we know P because we just calculated P, and then we just found out about Z, and then we have sigma sub P. We also calculated that. So we just plug in the numbers in these formulas. Okay. So let's do that. The upper control limit, lower control limit, P plus minus Z times sigma sub P. So these are the formulas. P is 0.025 or 2.5%. Plus minus Z is 2.17. 2.17. And the sigma sub P, I think is something like 0.01, something like that. I don't know the exact number, but you guys can figure out the exact number. Something like this. Any questions on this?
So
Yeah,
in the
okay.
test,
Yeah.
in the test, how many decimal point do we need to show?
2.
2.
Yes.
So, will for the test, will the z-score always be symmetrical?
Yes.
Oh, so
So-
how can we know which one is P sharp?
Q.
P sharp. Then.
Yes. I'll tell you exactly. Yes, I'll explain that. Okay. So, let's move to the next question. Let's move to the next question. So, what alpha risk would control limits of 0.047 and 0.003 provide. Okay? So here, they give us the upper and lower control limits, and they ask us to find the upper and lower control limits. Okay? So, in this case, we don't know what the alpha risk is. We don't know what the alpha risk is. But we know the upper and lower control limits. The upper control limit is 0.047, and the lower control limit is 0.003. Okay, this is the lower control limit. This is the upper control limit. Okay, so from here we can go find the corresponding z-value. Once we find the z-value, we can find this area under the curve to the left, and 1 minus that will be our tail probability.
And do we have to count with 2 to find the alpha? The tail probability?
Yes.
You have to multiply by 2.
Yeah, exactly. So now we're gonna rewrite these equations. Okay, so the z-value will be upper control limit minus p divided by sigma sub p. Okay. So let's plug in the numbers. 0.047 minus 0.025 divided by 0.11?
Yeah.
Okay, 0.011. So the numerator is then 0.022. The denominator is 0.011. So then the z-value must be 2. The z-value is 2. So I go from here to here. Z-values. So then let's look up the normal table, standard normal table. Okay. So 2. Okay. It says 0.9772. Okay. So the area under the curve to the left of z equals 2, it's going to be 0.9772. And the tail probability is going to be 1 minus that. Okay. So that's going to be 0.0228. So this is going to be 0.0228. Okay. 0.0228. So is everybody clear how I got this? Okay. So let's do the lower control limit. Okay. So the lower control limit, I'm just going to use the same formula. So instead of the upper control limit, I'm just going to change this number, 0.003. Yeah.
So in this case, Z is not symmetric, right?
It's symmetric. We're going to see it's symmetric.
Oh, it's minus 2.
Yeah. So when you take 0.003 and subtract 0.025, this becomes minus 022. Okay, divided by 0.011, this becomes then minus 2. Okay, so this z value will be minus 2. 2 minus 2 symmetric.
So in the test, we will have to find like the lower control limit because I will assume it is symmetric.
Yes, you can easily say that. You can just say it's symmetric.
So it's like
Yes.
Okay.
So since this is symmetric, okay, this will also be